Hey guys, how are we doing today? Happy St. Patty's Day. You guys ready for some linear algebra or what? Oh, sorry, I'm a couple minutes late. I was having some technical issues there. But anyway, you know, this is my way. I'm wearing this so I don't get pinched today. There we go. That's what I wanted to say. Oh, well, thank you. It took me all of 2 seconds to grow. All I had to do was put this hat on, which had it attached to it. So, you know, uh, truth be told, my facial hair doesn't really grow all that fast. It takes a long time. So, but anyhow, it would be cool to, have a beard like this at some point for a long time. All right, folks. So, how did quiz two go yesterday? Any questions about it? Went good? All right, cool. Well, today, I hope to keep it short and sweet. We're going to define the dimension of a vector space. Did I mention that yesterday that we were going to do that? Dimension that? I was kidding. So, yep, just front and back sheet of paper. We'll be discussing subspaces and their corresponding dimensions in a vector space. And then later on, we'll get more specific to dimension of subspaces in n space. All right. And then I was thinking that, with the time that's left over in class, you're welcome to stay in the session until class is officially over. I'll be hanging out in it. But if you want to work on any of that Wiley Plus, any of the Wiley Plus problem sets, and if you have questions along the way, I'll be sticking around in the collaborate session to help you guys out. All right, so it's optional. You don't have to stay, but if you want some instant feedback on some of the questions, from yours truly, I'll be happy to provide it. So without further ado, let's go ahead and take care of dimension. Yesterday, we fused a couple of sections together, namely sections 4.3 and 4.4. Section 4.3 was on span, and yesterday was, the day before yesterday was on linear independence. And we saw that in order for a set of vectors to be a basis, they not only need to span the vector space that they're coming from, but they also need to be linearly independent. And if a set of vectors satisfies both criterion, it forms what is called a basis. So we saw yesterday that R3 doesn't have only the basis consisting of the vectors I, j, and k. There were three other vectors that we were working with, v1, v2, and v3, and we established that they form the basis, meaning that we could rewrite vectors in R3 in terms of those new basis vectors. And it allows us to tweak coordinates of vectors or points that are in R3. I mentioned, or we had a little discussion on binary, how we could write the number 2 as 10 should we change the base from base 10 to base 2. So a basis is actually the foundation for the dimension of a space. And a basis for R2, one basis, would consist of the vectors I and j. And the number of basis vectors in the set is 2. And that happens to be the dimension of R2. A basis for R3 would consist of the vectors I, j, and k. This isn't the only basis. Okay, we had 3 vectors yesterday that were different from these that form the basis for R3. But whichever basis you look at, the basis consisted of 3 vectors. And that happens to be the dimension of R3. A basis for Rn would consist of the vectors e sub 1 all the way down to e sub n. And we can assume, just by looking at the indices here, that there are n basis vectors, which happens to be the dimension of n space. So hopefully you're seeing a pattern here. I want to give you a basis for a set of all polynomials of degree less than or equal to n. All right, this is the standard basis. You would need the number 1, the monomial x squared, and all monomials up to and including x to the n. Anybody have an idea as to how many basis vectors are in this set? Well, if we go by exponent, it might be tempting to say that the number of basis vectors is n, because that's the highest degree of the monomials. But there's actually n plus 1 basis vectors. And one way of seeing that is noting that the monomial 1 is the same as x to the power of 0. So in counting the 0, as well as the rest of the n monomials, there are actually n plus 1 basis vectors in here. So I'm just going to note that. Okay, so the number of basis vectors in this vector space is not exactly equal to, the subscript with our notation for the polynomial space. So before I officially define dimension, I do want to present to you a couple of results here. And we kind of had some evidence of this yesterday when we were looking at those basis vectors for R3. Number 1, all bases for a finite dimensional vector space, so you can think of n space or p sub n, have the same number of vectors. So for R3, if we're able to establish that a set of vectors is a basis for it, there's usually just only going to be 3 vectors for it. And part of the reason for that has to do with the next result. It says, let V be a finite dimensional vector space, and V sub 1 through V sub n be any basis for V. Part A says that if a set in V has more than n vectors, then it is linearly dependent. Okay, and what that means is one of the vectors in the set can be written as a linear combo of the other. As an example, let's say I considered a set S of vectors in R3, and I'll use I, j, and k, but in their component form. The components of I, 1, 0, 0, j would be 0, 1, 0, and k would be 0, 0, 1. And let's say that I put another vector in here. Say it was 1, 2, 3. This right here, the set S, it has more than 3 vectors. Okay, and the n that they're referring to here would be the dimension of the vector space that we're pulling these vectors from. So with this set S, each of these vectors has 3 components, so we're pulling them from R3. Now, in this case, n is equal to 3. That's because we're in R3, and there are 4 vectors in the set S. Now, anybody want to tell me why this set S would be linearly dependent? So the reason why it's linearly dependent is because, I'm sorry, was somebody chiming in?
Yeah, so I think after we calculate all these vectors, we can get, we are not going to get any zero because we have 1, 2, and 3.
Right.
And if we keep adding, it will give us a real number, not a zero.
So yeah, it does have to do with 1, 2, 3. Um, 1, 2, 3 happens to be a linear combination of these three vectors. So remember, if a set is to be linearly independent, then no vector in the set can be written as a linear combination of the others. Right? But we could easily write 1, 2, 3 as 1 times the components of I plus 2 times the components of j plus 3 times the components of k. So that right there establishes that this set of vectors is dependent. Now let's kind of look at it, from a different viewpoint. In part B, it says if a set V has fewer than n vectors, then it does not span V. So now let's say that I tweak that set S by removing a couple of vectors. And let's say that I leave the vectors I and j in the set S. Okay, keep in mind, in this example, our vector space V is R3, which implies that the value of n is equal to 3. But we've only got 2 vectors in the set S. So the conclusion of part B is that if the set in V has fewer than n vectors versus more, then it does not span V. So according to this result, my set S here will not span all of R3. Any ideas as to why that might be? Other than, it's the result of the theorem.
Um, I would say because no matter how you combine the two vectors in S, the third component will always stay at the origin, so you won't be able to span like vertically, I guess, in the third dimension.
Perfect. Yeah, that's exactly right. Yep. And actually, I think I can draw some of this out so you guys can visualize it. It's my three-dimensional axes there. Vector I will be 1 unit long, going along the x-axis. The vector j will be 1 unit long, going along the y-axis. Any combination, linear combination of the vectors I and j is going to just generate a plane, namely the xy plane. So what I have shaded right here would be the span of our current set S. So by having a set S with fewer than n vectors, we end up shaving off a dimension, don't we? The dimension of the span here is only two-dimensional, and there would be no way that a two-dimensional object, like this, that's fixed in the xy plane, could create that third dimension, like you were saying, Sammy. So yeah, we can actually be a little more specific about the span of S. The span of S is equal to the xy plane in this case. So yeah, the span here only creates a two-dimensional object, which is why S could not span R3 in this case. So with that, the dimension of a finite dimensional vector space V, which has the following notation, dim of V, is equal to the number of basis vectors for that vector space. And in the special case of the zero vector space, we say that that has a dimension of 0. So in other words, if we were to write dim of, and the zero vector space can just be written as the zero vector being in set notation, that would have a dimension equal to 0. So again, the dimension of a finite dimensional vector space would consist of the number of basis vectors for that vector space. Now we looked at the standard bases for a few vector spaces. The first one was for R2, which consisted of I and J. Those aren't the only two basis vectors though. But regardless, no matter which basis you have for R2, there's always going to be two basis vectors. So the dimension of R2 is 2. The dimension of R3 is 3. Anybody want to type in the chat what the dimension of Rn is? Yep, n. All right. Careful on this one. What is the dimension of P sub n? You got it. Now, the dimension of the set of all matrices that have a size m by n is equal to the product of m and n. And to illustrate that, we looked at a basis for m sub 2 yesterday. The basis for it had 4 matrices. Here was the first one. Here's the second. Here's the third. And here's the fourth. Now that's 4 basis vectors for the basis for m sub 2. And if you multiply the two values here, the subscripts, you get the dimension. So we could write dim of m sub 2 is equal to the product of those two 2's, which is 4. And that's the number of basis vectors. So far, so good? Anything confusing you? Anything I can clarify? All right. So we're going to look at some of those subspaces that can be formed in R3 and tie in their corresponding dimensions. So it's important to note here that our vector space B is equal to R3, and R3 has some subspaces. The very first is the origin, or the 0 subspace, which we learned on the last page that the 0 subspace is 0-dimensional. Okay, so that would be a vector subspace consisting of just the origin, or the 0 vector, and that's 0-dimensional. Another subspace of R3 would be a line through the origin, which is in blue right here. Okay, and we know just by basic geometry that a line is 1-dimensional. Another subspace is a plane through the origin, okay, which we have that kind of in gray, and a plane is 2-dimensional. And then of course we could have all of R3 itself, which we know is a 3-dimensional vector space. The reason why I'm mentioning all this is to give you an important fact about the dimensions of subspaces. Let's make a note. Let's say if W is a subspace of a vector space V, then the dimension of that subspace, the dimension of W, will always be less than or equal to the dimension of the entire vector space, the dimension of V. All right, so I'm going to label each one of these subspaces. I'll start with the origin, or the 0 subspace. I'm going to call that W sub 0. And then I'm going to call the line through the origin W sub 1, the plane through the origin W sub 2, and then all of R3, we were calling that V at the start of this part. Now, if you look at the dimension of the 0 space, that is definitely less than or equal to the dimension of the whole vector space, which is R3. It also happens to be less than or equal to the dimension of W sub 1 and W sub 2. In fact, we can chain link all these vector spaces dimensions in the following way. The smallest dimension is the dimension of the 0 subspace. I'm going to write dim of W sub 0. This is less than or equal to the dimension of the line through the origin, which is 1. So I'll say less than or equal to dim W sub 1. And both these happen to be less than or equal to the dimension of W sub 2. And all three of these happen to be less than or equal to the dimension of the entire vector space, V. And the point of all this is it's helpful to have a visual of these different subspaces, especially in R3, because there's a strong connection between these subspaces and homogeneous linear systems that we can form within R3. And another thing too is, it kind of gives you a way of checking your work. If you're working in R3 and you solve a problem and end up with 4 basis vectors, then there's a chance that one of those basis vectors is redundant, in which case you can remove it, to get the minimal set of vectors needed, to span that subspace. In fact, our last example is going to be on subspaces of R3 as it relates to homogeneous linear systems. Right here it says find the basis for the solution space of the homogeneous linear system. And then we'll go a little bit further to find the dimension of that space. Now, since we are working in R3, which might be worth noting, our vector space V is R3. The possible objects that we could get, which correspond to our solutions, could be the 0 vector space, it could be a line to the origin, it could be a plane to the origin, or it could be all of R3. All right, so this kind of narrows down the kind of object we would get solving a system like this in R3. So let's just kind of go through some of the stuff we would normally do. I'm going to convert this into augmented matrix format. Top row 1, -3, 1, 0. Second row 2, -6, 2, and 0. And then 3, -9, 3, and 0. And I'll request that you folks go ahead and get this into the graphing calculator and RREF it. And in about a minute or so, I'll ask for somebody to share their RREF version of the matrix, and then we'll continue on from there. All right, anybody want to share their row values? Or perhaps maybe you can confirm them along with me. I got 1, -3, 1, and 0 for the first row, and then everything else is full of zeros. A confirmation on that RREF version of the matrix? Sweet. So keep in mind what these columns refer to. Column 1 relates to the variable x, column 2 y, and then column 3 z. And by now I'm sure we know how to jump out of this into a solution format. X corresponds to a leading 1. Unfortunately, y and z do not. So what that means is, if we want to write the general solution to the system, we're going to need parametric equations. And more specifically, we'll need two parameters in order to define them. Maybe we'll have y equal t and z equal s. And so business as usual for defining our PEs, we'll say let y equal t, z equal s. You can rewrite row 1 with these parameters, x minus 3t plus s equals 0. And solving for x equals 3t minus s. So the parametric equations corresponding to the system, x equals 3t minus s, y equal t, and z equals s. Now we're going to go further. A general solution to this, and this is something we did not too long ago. A general solution could be written as a vector with these three components x, y, and z. But like we were doing before, I prefer to rewrite this in terms of the parametric equations. So the first component would consist of the expression 3t minus s. The next component will consist of the parameter t, and then the final component will consist of the parameter s. And do you guys remember us kind of like dissolving this single vector into a sum of two or more vectors a little bit ago? In this case, we can break this up into two separate vectors because there are two parameters in the mix here. Okay, we have a vector that we could make just using the parameter t, and a vector that we can make just using the parameter s. I'm going to give you a moment to see if you can break this up into those two vectors. All right, and I'll check in with you in about 30 seconds or so. the first vector, I'll base it on the parameter t, 3t, t, and 0, added to a vector based on the parameter s, about negative s, 0, and s. Sending out an SOS. I'm going to go a little bit further with this and factor out the parameters. Okay, I'll take a t out for first vector. Leaves behind these components, 3, 1, and 0. And then I'll factor out the parameter s from the second vector, which leaves behind negative 1, 0, and 1. So it appears as though the solution space would consist of all vectors that can be written as a linear combination of the vectors 3, 1, 0 and negative 1, 0, 1. Okay, so by splitting up, here I'll highlight it. By splitting this up into two vectors corresponding to the two parameters, any solution to this homogeneous linear system has this format, which is basically a linear combination format in disguise, right? You can think of T and S as the coefficients of the linear combination. And what are we forming mixtures of? Well, we're forming mixtures of the two vectors 3, 1, 0 and negative 1, 0, 1. i.e., all solutions to the system can be thought of as being based on the vectors 3, 1, 0 and negative 1, 0, 1. So back to chapter 3 stuff, this is like a vector v1, and this is a vector v2. And if we wanted to go a little further with this, we could add in the 0 vector from R3, and that would tell us what kind of object this is. This is actually a plane going through the origin, okay? And these two vectors, v1 and v2, build that plane, by virtue of linear combinations of them. Let's state our answer then. Our basis will consist of the set of v1 and v2, 3, 1, 0, and negative 1, 0, 1. Okay, this would be our basis because these two vectors construct that plane through the origin. Anybody want to tell me what the dimension of this basis is? Oh. Let's maybe call this basis W, and the dimension of W not R3. Keep in mind how we define basis on the last page. The basis, the dimension consists of the number of basis vectors. Not R2, simply just the number 2. So the dimension of our solution space is 2. It's 2 because we have 1 and 2 vectors in the basis. Yep. And that's all I have for you folks today. You have any questions about this section? All right, I'm going to stay in the session if you want to take this time to. Yeah, I can back up. Page 1, do you need? Okay. Where do you want me to stop at? You want me to go to the top of it or bottom? Okay. Is that good enough? No problem. So yeah, you guys are welcome to leave the session, or you're welcome to stick around until class is officially over. I think that would be a good a good use of your time might be to you know open up the problem sets from Wiley Plus and work through some of the problem sets. That way, I can be here to help you through them in case you're running into any trouble. All right, but that's optional. If you guys want to leave class a little bit early, I won't judge you. So, I'll leave it up to you, but I'm going to be in the session until class officially ends. All right, just to be here to answer any questions that might come up. All right, so if you're taking off, then I will see you tomorrow. Enjoy the sunshine, and I will wait in great anticipation of our next section that we'll do 4.7. No problem.
I'm sorry, but can you show us how to do RREF in calculator? I know
Yeah,
you did it, but I just forgot kind of.
no problem. All right. Is it okay if I do it with this matrix?
Yeah, that's fine.
Okay. All right, so we'll press second and then the X inverse key. And are you seeing this menu?
Yes.
Okay, let's go to the edit column. This is where we can create this matrix. I'll select matrix A. You can press enter. It brings you to this screen, and the calculator wants to know what size of the matrix it's going to be using. So there are 3 rows and 4 columns in this augmented matrix. So I'll press 3, enter, and then 4, enter. And now we'll just enter all of the values according to what we wrote down. So each time you enter an entry, you do want to press enter afterwards. That way it stores it in that slot. 3, -9, and 3. So let me know when you have all of your entries in there, and I'll tell you what to do next.
Okay.
All right, so we're going to go back to the home screen. We'll press second mode, and we're going to go back into the matrix menu. So second X inverse. All right, let's arrow over to the middle column for math. And we're going to hit the up arrow key until we get to option B. So let me know when you're there.
Yeah, I see that.
Okay, go ahead and press enter.
Okay.
It takes you back to the home screen, and now we're going to put our matrix A in here. So we'll have to press second X inverse again. And this time we're going to select A from the names column. And as you can see, we have the matrix defined. So when it shows you the size of the matrix, that's an indication that you've defined it. So go ahead and press enter. You can close off parentheses and then enter one more time. And that should be the RREF version of the matrix A.
I see. Thank you so much.
No problem.